What happens if I ask ChatGPT what's my dog's name? ChatGPT doesn't even know if I have a dog or not. So let's see. Okay, I don't know what's your dog's name yet. If you tell me, I can remember for future conversations. So let's tell it my dog's name is Test, just for the sake of testing. Okay, interesting. Got it. I'll remember your dog's name is a Test. And it has been saved into memory. Now let's open a new chat and ask the same question. Okay, your dog's name is a test. So how did it do that? By default, large language models do not have access to external knowledge sources like the name of my dog or whether I have a dog or not. To solve this limitation, we need to give it an external knowledge source. In that case, was the memory of ChatGPT. So whenever we ask it a question, it's going to convert it to a query and then try to retrieve some knowledge to put it in the context window of the large language model to answer the question correctly. This is called RAG, or Retrieval-Augmented Generation. This model consists of two main components. The retrieval model, which basically tries to retrieve or fetch the knowledge on the information from the knowledge source. And we need a large language model, which is in that case, it was GPT 5.2, that used that knowledge and gave us the final answer. So now let's implement simple, local, free RAG pipeline that we can run locally in our computer. So first, with the user ask a query, we're going to run it through an embedding model. The output of the embedding model is going to be saved in the vector database. We're going to fetch the knowledge from the vector database and give it to the chatbot or to the LLM, and then the LLM is going to return the response based on that. So first we need the embedding model. The embedding model converts text into vectors, into a list of numbers. You can think of it as converting our text dataset into high dimensional vector space. And that vector space basically represents the semantics of our text dataset. Every vector in the embedding space will represent a text chunk from our dataset. And if two vectors in this embedding space are close to each other, so if they are more aligned to each other, then it means that they are semantically similar. That's how the embedding model works. I'm going to recommend you a video by 3 Blue 1 Brown that explains this concept visually of basically the word embedding or the vector embedding, how we can basically convert text into a vector and how we can put it into high dimensional vector space. Okay, now after we have all our vectors, we're going to save it in a vector database. We're going to just store the vectors in a way that facilitates search when we basically do the retrieval or the fetching of the vectors. And then we need a chatbot, which is just a large language model. In our case, also we're going to be using free open source model that I'm just going to run locally in my computer. To do that, first we need to do the indexing. So we need to take our knowledge source or our dataset, our text dataset, and we need to convert it into vectors. First, I need to split it into chunks. And every chunk is gonna pass through the embedding model to convert it into a vector. And then all the vectors are going to be saved in a vector database that can just be simply a list of vectors. So for example, Italy and France produce over 40% of all wine in the world. This sentence has been converted by the embedding model into an embedding vector, which is just a list of floating point numbers. So now we have our vector store, which is just a list of vectors. Then we need a way to do the search, to fetch the information that are relevant to our query. How do we do that? We do that using cosine similarity, taking advantage of the fact that vectors in our embedding space are aligned based on the semantic similarity. The smaller the angle between two vectors, the more aligned means that they are more semantically similar. Okay, now the retrieval phase. So the retrieval is done by first vectorizing the input query by the user and converting it into a query vector. And then we run it against our vector space or our vector database to retrieve or fetch the top n relevant chunks from the database. And then we give it into the context window or to the knowledge of the LLM, and then the LLM is going to use that knowledge and return the response to us. Okay, so now let's take a look at the code. First, we need to basically load the dataset. We take the dataset from here, wget. So now let's take a look at it. Basically just has some facts about cats. So on average, cats sleep 2/3 of the day, and we're going to test the knowledge of the model using this dataset. Okay, so now the first thing that we need to do after we have the dataset to split it into chunks. In this case, every line is going to be a chunk in the dataset. So we read the lines and then convert it into a list of chunks. After that, we define the embedding model and the language model. So for the embedding model, I'm going to be using Qwen3 embedding model, one of the best open source embedding models, and it's relatively small, 600 megabytes. You can take a look at the embedding models leaderboard and you can choose the model that fits your task. For example, for clustering, classification, pair classification, re-ranking, retrieval. In our case, our problem is retrieval, and Qwen3 actually is a small model that scores high 8th place in the leaderboard. So we're gonna go with it. To do that, I'm gonna be using Ollama. After you install Ollama, you can just run Ollama pool 0.6 model now has been installed. You can verify that by running list coin3 embedding. The size is 639 megabytes, exactly as written here. Take the name of the model, we'll put it here, and then the LLM. I'm gonna be using Llama 3.2. 1 billion parameter model. Now we need to build our dataset. So to build our dataset, we need to take every chunk and pass it through an embedding model. To apply the embedding model step, we need to run ollama.embed using the embedding model and then the input chunk, and then we take the embedding to append it to the dataset in addition to the chunk itself. So we take the text and the embedding, we add them to the dataset. Okay, so now we iterate over the dataset and we just run this function to add the chunk to a dataset. So this is gonna just basically convert it into a vector and is gonna save it to our vector database, which is just a list. Every line in this dataset is just going to be converted to a vector. So we're going to have just a list of vectors. So now we need the similarity function, which is a cosine similarity. So the cosine similarity, as we explained, is just the dot product of the two vectors divided by the product of the norms of the vectors. So now we have the retrieval function. So the retrieve function takes a query and the top k. The top k is basically going to decide how many relevant documents or vectors are we're going to be retrieving based on the query. First, we're going to take the embedding of the vector and convert it into a query vector. So here we basically have after that the query vector. We basically iterate through the vector database and we calculate the similarities of the two vectors. There are actually more advanced or like more optimized ways to do that by basically having an index and approximate nearest neighbor search. But for the sake of this video, I'm gonna do it basically in brute force manner. Just gonna iterate over the vectors and calculate the similarity. I'm gonna be sorting the vectors by the similarity. So we run the retrieve function. This is gonna give us the retrieved knowledge. And now we just print the retrieved knowledge with the similarities. And now we need to generate the answer. So now we have actually the knowledge. Now we need to give it to the to our LLM, which is Llama 3.2, and then we need to generate the response. So the prompt to the LLM is very simple. You are a helpful chatbot. Use only the following information to answer the user question. Do not make up any new information. And then we give it most similar text chunks from the retrieval process. Okay, so now we need to run the chat. We need to stream the output. So we run ollama.chat. We pass the language model, and then we give it the system prompt, which is the prompt that we just defined here with the knowledge, and also the input query, which is basically how much do cats sleep. So let's run the function. Okay, so now let's see the results. The query was how much do cats sleep. Here are the retrieved documents. Cats sleep 16, 18 hours. This is the first document. The second document is on average cats spend 2/3 of every day sleeping. That's also correct. The third one, one reason that kittens sleep so much. So it's also about sleep. So the retrieval is actually working correctly. And let's see the final response by the LLM. Cats are notorious sleep lovers and they spend significant amount of time snoozing. According to various sources, on average, a healthy adult can sleep 16 to 18 hours. That's exactly from our data set. Also, they sleep 2/3 of their life, which means that the most time devoted to rest. This is because cats are natural predators. They require plenty of energy for hunting and fighting. So we have built a simple retrieval system that builds a data set from a text data, converts it into a knowledge source of vectors, and then basically whenever we ask it a question, we can basically convert that question into a vector and then retrieve the top relevant chunks, and we can get an answer based on that dataset. Here are things that we can improve in the future. For example, we can let the LLM itself choose the query, not pass the direct user query. Because the direct user query could be a follow-up, and in some cases that could break the pipeline. Also, now we choose the top n results based on the cosine similarity. Now we need to re-rank them. When we re-rank them using a large language model, for example, the results are going to also improve. Also, the dataset is stored in memory, as I told you. We can store it in a persistent storage, and we currently consider each sentence to be a chunk. So this is not also correct. We can also use some semantic chunking. So we can divide our big text corpus into chunks based on the semantics as well. Also, the language model that we're using is 1 billion parameter model, so it's a small model. If we use the large language model, the results will also improve. So yeah, that's all I wanted to share with you in this video. Thanks so much for watching. See you in the next one. Bye bye.